Hello everyone, welcome to Chapter 5 on probability and random variables. In previous chapters, we talked about the collection of data, we talked about data types and studies, we talked about graphs, and we talked about organizing data in tables as well as looking for means, medians, standard deviation, as well as being able to find a correlation between two variables. So suddenly we veer off into a different topic that seems unconnected in a way, probability and random variables. But if you think about it, probability actually has a very central role in the way that we interpret our statistics, especially when it comes to inferential statistics. So in this particular chapter, we're going to concentrate on the idea of probability, and we'll roll probability into our discussions in later chapters about its role in how we come to conclusions about how well a sample actually does represent a population. But first, we need a few basic ideas right here, and so we're going to talk about some of these basics as they happen. One of the first principles that we have to know about probability is its definition, and we define it this way. We say, what is the probability for equally likely outcomes? So let's suppose we have an experiment that has n possible outcomes. All of those outcomes are equally likely. Well, in an event that can occur in f ways can have a probability of f over n of occurring. A very simple experiment would be when we flip a coin. We know that if we flip a coin, we think about heads versus tails, there are n equals two possible outcomes. Both are equally likely if it's not a weighted coin or something like that. And so there would be one way of getting a head or one way of getting a tails, and so our probability of getting a head or a tail is 1/2. Well, let's talk about another type of experiment, one that we're also pretty familiar with right here. We'll talk about the idea of cards in a regular playing deck. Right? So we have a deck with 52 cards in it. There's four suites: spades, hearts, diamonds, and clubs. And each suite has 13 cards, right? So 13 times 4, that gives us 52. Spades and clubs are black, hearts and diamonds are red. So there are two black suites and there are two red suites. If one of these cards is selected at random, what is the probability that it's a spade? Well, let's think about this. If we wanted to find out the probability that it was a spade, we think that the spade is one of the four different suites. And there are 13 cards that would be considered spades. And if it's equally likely for us to draw a spade as it is to draw any other card, we would say 13 out of 52. If we express that as a probability, we would want to reduce this. Either as a fraction, we reduce this fraction, both 13 and 52 are divisible by 13, and so we would say that's 1/4, or the probability would also be expressed as a decimal, 0.25. Okay. How about this one? How much is a red? Well, let's see. We said there were two suites that were red, right? So red, we could have both hearts. Let's see, there are hearts, and there's 13 of those, and then there's diamonds. Diamonds, there are 13 of those. Make a total of 26, right? So our probability would be 26 out of 52 total cards, and if we reduce that, of course, our probability comes to be 1/2, which we could write as 0.5. Right? So we see what's happening is that we're getting a fraction that represents the probability of the number of ways that a thing could happen divided by the number of possible outcomes that we could get. How about this one? What if we say it's not a club? Well, now this one's a little bit different, but let's think about it. There are 13 clubs in the deck because that is one of our four suites. Out of 52 cards, right, that means 52 minus 13, that's going to be, let's see, 39, right? 39 ways in which we might not be able to get a club, right? So we would say if it's not clubs, there are 39 non-club cards out of our deck of 52, and if we divide everything by 13 again, we're going to find that we have 3/4, right? As a decimal, we would represent that as 0.75. All right. So the idea right here is we talk about the probability, right? 3 out of every 4 cards is not a club, or there are 39 out of a total of 52 cards that are not clubs, right? So when we say not a club, right, we think about the way that we set this up. Here's another example. This one's a little bit more complex. According to the problem, a family is defined as a group of 2 or more persons that are related by birth, marriage, adoption, or residing together in the household. So according to the current population survey published by the Census Bureau, the size distribution of families are as follows, with the frequency in thousands, right? So 37,148,000 families have a size of 2, and we see the relative sizes of each of those. Well, what do we have to do? We think about if it's equally likely for us to be able to get any size family, right, 7 plus all the way down to 2, we think about the way that we could possibly get those. And we're asked, well, let's find the probability that a family has 2 persons. Well, what we're going to do is we're going to add up the total frequency right here. So we should get out our calculator and check this out, right? So we're going to go ahead and we're going to add our numbers here. So I'm going to take 37,148, add 17,810, and so on down the list. And that means we get a total of 80,505 ways that we can get this particular frequency. So 80,505. All right. So if we wanted to find out what was the probability that we're going to get a 2-person family, our probability would be found by taking 37,148 and dividing it by 80,505. Right? Now, fractions like these are a little bit harder for us to deal with, so we would just go ahead and carry out the division and get this fraction, 37,148 divide by 80,505, and that gives us a probability right here. And we're going to express these into 4 digits, 0.4614. So 0.4614. 4614. I'll get my eraser here and fix that little leaky pen there. There we go. Okay, so that's our. How about more than 3 persons? What should we do there? Well, if we say more than 3 persons in a family, right? More than 3 means greater than 3, right? So we're talking about 4, 5, 6, or 7 more, right, in a family. So what we would do there is that we would add up all the possible ways that we get families of greater than 3 in them. So we would add up our last 3 right here, right? 15,054 plus our 660, 6,660 plus all these other numbers, which in this case is going to be 25,547. Of course, if we want our probability, we're going to divide that again by the total of 80,505 and get the equivalent decimal to that one for this probability. In this case, that works out to be 0.3173. How about this one? Between 1 and 3 persons inclusive. Between 1 and 3 persons inclusive. So, do we have any families of size 1? No. But this question we're talking about, between 1 and 3, so that means we could have 1, we're really saying 1 or 2 or 3. So that really what we're doing is we're going to add up these families that have 2 or 3 and figure out the fraction right there. So if we add 0 families that have 1, 37,148 that have 2, and 17,810, and then divide that all by 80,505, here's what we'll find. 54,958 divided by 8,505, or 0.6287. How about D? That's sort of a weird one. It says, it asks, well, how many families in this survey have one person? Well, the answer, of course, is that there are 0. So what would we say here? Well, for our probability, there are 0 ways out of 80,505 families in our survey found, so we would say that that probability is 0. Can we have a probability of 0? Sure, why not? Probability of one or more person? Well, there were all the families had more than 80,505. So in that case, our probability would be 80,505 families divided by 80,505 families. Well, the long story short is that that means that there is exactly a probability of 1, or 100%, that that's true. Well, that's sort of an interesting thing to see. Okay, so more to come in the next videos. After we talk about just one more basic set of probabilities, some properties. Well, there are some probabilities, and we just saw this in our last example, that first of all, the probability of an event for all of our probabilities were between 0 and 1. We didn't have any probability that was less than 0, and no probability that was greater than 1. And we saw that it was possible to get 0, and that was if the event was unable to happen. We didn't have a family of 1. That was called a single person, not a family. And of course, the probability of an event that must occur, that is, a family has more than one person in it, right, that must be 1. So all probabilities between 0 and 1. So strictly speaking, this statement, the probability of a baby being born is 50-50, well, we know what they mean, but what are we really asking? Well, if we wanted to state it correctly, according to property 1, that event has to be between 0 and 1. When most people say 50-50, they mean 50%, right? So we typically write 50%, and by 50%, of course, we mean as a decimal 0.5, or stated another way, we might say 1/2 instead. So really what we're saying is that the probability of a baby being born a boy is 0.5, or 1/2, right? That 50-50 business just tells us that we mean, well, there's a 50% chance that he is, and a 50% chance that the baby is not a boy, right? So there we go.